All right, let's go over this question from the discussion sheet. A space station is constructed in the shape of a wheel. So let's go ahead and start drawing our picture here. So we have this space station constructed sort of in the shape of a wheel. Boy, that's really bad. Apologies, let me just try doing that one again. We'll make the wheel like this. 22 meters in diameter, so I'm going to say the radius of this guy is 11. That's what I'm getting from that piece. Has a weight of, or a mass, 5 times 10 to the 5th kilograms at the rim. Once the space station is completed, it's set rotating at a rate such that an object at the rim experiences a radial acceleration equal to Earth's gravitational acceleration g. So you may have seen this in sci-fi movies. It's this idea of like a little space station that starts rotating. Let's say that it rotates this way. It's got some angular velocity omega, and it rotates such that a piece here, somebody here on the sort of outer at the rim experiences a radial acceleration equal to g. And the idea being that basically if you sort of live in this little rim area, then you basically have the same acceleration that we do here, and it feels normal to you. Okay, so then to accomplish this, 2 small rockets are attached to opposite sides of the rim. So let's say like one here and one here. And so if we're rotating in this counterclockwise direction, then that means that this rocket would apply force kind of like that. And that rocket would apply force kind of like that. The force at each rocket is 100 newtons. And so we want to know how long will it take to reach the desired rotation rate, and how many revolutions will the space station make in this time. So again, we like to kind of just pause. So if you want to maybe pause this and try working out a little bit of this, see how far you can get, and then we'll come back and we can discuss. Okay, so sort of the idea here is that, again, we want our centripetal acceleration for somebody on the rim, and again, this is this thing with radius r of 11 meters, to equal g. So I'm going to use the equation for centripetal acceleration where it's omega squared times r, and equal that to g. And so if I then solve for the omega, and here I'll put in this as the capital R. So again, this is a point on the rim, so you get to, again, feel g as your acceleration. And so we're going to get here g divided by r square root. So that's our goal omega. So I'll call that the omega final. And in this problem, we're said that it starts at rest, and so its omega initial will be 0. So this is what we got here. And so how long will it take? Well, since we know our final omega, what we want to do is try to find our angular acceleration. And how are we going to do that? Well, we're going to use the sum of the torques equals I times alpha. So our Newton's second law when looking at rotations. And so over here, I'm going to kind of go through and look at this. So again, so here's our axis. So again, we're going to use this as our axis because basically our things going to be rotating about that axis. And so we're going to use that. And so we look here at our 2 forces. And so I'll do the same sort of thing I've always done. Or a similar thing, I'll draw this line of action through the force, and then hopefully you see this is just one of those sort of cases where basically the shortest distance between that point and where the force is, and of course the force is sort of more acting right here, right on the rim, would be that radius arm, r. So the moment arm is going to be that r. And so here we would have for the torques, it would be the force of 100, and I'll go ahead and make this white so we can see it a little bit better. So FR, and then there's a 2 because there's 2 of those rockets. So basically the torque in this situation is caused by the 2 rockets, and they're a distance r from the center, and so they're going to give a torque of 2FR. And then I equal that to I times alpha. Again, in this case, so mass times r squared, our moment of inertia is the moment of inertia of a hollow cylinder. And so again, I'd say hollow cylinder. If you look this up on our charts or online, it's just mr squared. And then we have our alpha. And so if we solve for our alpha, which is kind of what we're looking for, so I'll have 2FR and then divide by mr squared. This r will cancel with one of them from over there. And so we have an angular acceleration of 2f mr. Now you could stop here and calculate a number here if you want, I'm just going to leave this in terms of letters for right now. But that's our angular acceleration. This is our omega final. And so now in the question, we're asked how long will it take to reach the desired rotation rate and how many revolutions will it make? And so let's write those two pieces of information we sort of got. So our omega final is radical g over r here, and then our alpha, if we go back, is 2f over mr. So 2f over mr. So now this becomes a kinematics problem. And so for instance, we can do this a couple different ways, but probably the easiest, let's go for the time first. And so here's one of our kinematics equations. So again, omega final is this guy. Omega initial is given as 0, so it's starting at rest. And then alpha times time. So if that thing goes away, then my time just works out to be omega final divided by alpha. And so omega final I'll write as radical g over r. And that's going to be divided by our omega, which I'll write as 2f over mr. So if I bring the mr upstairs, I end up with something along these lines here. M over 2f, that's from the m up there, and it'll be times radical gr. All right, and then I just plug in the numbers. So the mass is pretty big. It's 5.0 times 10 to the 5th kilograms. So that's it for the mass. 2 times the force. The force is 100 newtons. And over here it's radical g, 9.81 meters per second squared, and then times that r of 11 meters. And when I went through and calculated this, I got 2.59 times 10 to the 4th seconds. So that's the first thing we're looking for, was the time. Now the second thing is we want to find the number of revolutions, which again is a kinematics equation. If you would like, go ahead and pause here and give that a go, and then we'll talk about it. All right, and then so again, our sort of two key pieces here we're using is this here. So 2f over mr for the angular acceleration, and then omega final is radical g over r, and then omega initial is 0. And now for this case, I'm going to use this particular kinematics equation, and here we're solving for the change in angle. So again, we'll call omega 0 to be 0, and so if I go through and solve this, I get change in theta is going to equal omega final squared divided by 2 alpha. And so if I plug in my numbers up here, I get rid of the radical sign because we square the omega final, and then down here it would be 2 times 2f mr. And so if I bring the m and the r upstairs, this ends up being mg over 4f is what I get with my algebra. And so we go through, and again, we'll write out our numbers. So 5 times 10 to the 5th kilograms, that's a 5 in there, times 9.81 meters per second squared divided by 4 times 100. So again, just plugging in the numbers from over here. And when I did this one, the number I get is 1.226 times 10 to the 4 radians. And this, the last step is here. They're asking how many revolutions. This is radians. This is actually, the angle. And so for the last step to do that, you would just take this number here. And so revolutions would equal 1.226 times 10 to the 4 radians divided by 2 pi. And when I plugged that in, I came out with something like 1951 revolutions. So that's sort of the idea of this one here. Again, so we're making this space station that can kind of mimic Earth's gravity, and so they wanted to know a couple things about how long it would take to kind of work up to there. All right, hope this helps. Thanks.